physics, we study systems that seem complex, objects that spin, structures that oscillate, and particles that behave unpredictably. But behind that complexity, there is often a simple, elegant pattern the system naturally follows. That pattern reveals itself through the behavior of eigenvectors. Eigenvectors are special vectors that do not change direction when a matrix transformation is applied. They're just scaled by a number called an eigenvalue. Now let's define eigenvectors and eigenvalues more precisely, the way they're classically introduced in mathematics. Assume a linear transformation in 3D space that rotates and scales vectors around a fixed axis by an angle theta. Let's see what happened to the vectors. So we have vectors here, and under a linear transformation, those vectors look like this. Some of them change directions, some of them change both directions and magnitudes. But remember, eigenvectors stay on the same line. They keep their directions. Let's look at the pink vectors. As you see, it kept this direction, and it looks like nothing happened to it because it got scaled only by 1. And let's look at the blue vector. It kept its direction, but it got scaled by 3. But let's look at the red vector. It didn't keep its direction, so it's not an eigenvector. If we call the transformation A and the vector V, this is what our equation should look like. This basically says that applying A to V is like multiplying V by some number lambda. So this is our equation. To find its eigenvectors and eigenvalues, we need to rearrange this equation into this. First, we need to find the eigenvalues, lambda, and plug each of them into the equation to solve for V, the eigenvector. And since we're looking for non-zero solutions, the matrix has to be singular. And a matrix is singular only when its determinant is 0. So we solve for determinants A minus lambda times the identity matrix and set it to 0. This equation is called the characteristic equation. It gives us the lambda, eigenvalues, and eigenvalues enable us to solve for V. Okay, let's solve an example together. Suppose we're given this matrix and we're asked to find all the eigenvalues and their corresponding eigenvectors of the matrix. First, we need to find the eigenvalues, which means we need to solve for the characteristic equation here. And the identity matrix scaled by lambda is, and as the equation says, we need to subtract lambda I from A, which is this, and we need to find the determinant of this, which means we need to multiply these two together and subtract it from the multiplication of 1. Then we find this equals to 1, which means lambda is either 1 or 3. So these are our eigenvalues. So now we have our eigenvalues, we can find our eigenvectors. To do that, we need to plug each of them into the equation here. Remember, this is the characteristic equation, A minus lambda I. And this has to be 2 minus 1, 1, and 1 stays the same. This one stays the same too, and 2 minus 1 is 1. Then we can find our eigenvectors by setting the equation. So this is what we just found, and this is the eigenvector. And we need to equal it to 0. So from either row, this is what we get, which means x equals to negative y. So our first eigenvector has to be 1 to negative 1. Let's do the same thing for the second eigenvalue, lambda equals 3, which is 2 minus 3 is negative 1, and this one stays the same, this one stays the same, 2 minus 3 is negative 1. So we set the equation again. So from either row, we have this, which means negative x equals to negative y, x equals to y. And if we choose 1 for x, y has to be 1 too. So our second eigenvector has to be this. Okay, now we know how to solve an eigenvector and eigenvalue problem. We can talk about the practical applications. 3 major examples include structural vibration analysis, computer graphics and simulation, quantum mechanical systems, and many more. But we're going to expand on the first one. Every structure, whether it's a bridge, an apartment, or a bookshelf, has certain ways it naturally tends to vibrate. These are its natural frequencies expressed as eigenvalues. Their specific shapes of motion occurring at those frequencies are the eigenvectors. If an external force like wind or an earthquake matches one of those frequencies, it can cause resonance, dramatically amplify the vibration, and collapse the structure, which has happened in history. To prevent such disasters, engineers calculate these values to design safer structures.